So the first basic question is saying that I have 100 centimeter cube of a 1 molar HCl solution that was mixed with 100 centimeter cube of 1 molar NaOH. That's 20 degrees centigrade, and the temperature has increased to be 26 degrees. This happened in a coffee cup calorimeter. Calculate the delta H for the reaction. And he wrote the net reaction, which is H plus OH minus, give us H2O. Assume that the density of the solution is 1 gram per centimeter cube and its specific heat capacity is 4.2 joules per degrees Celsius. So we have that givens are the volume of HCl is equal to 100 centimeter cube. Since we are going to work with molars, so we have to change this one into 0.1 decimeter cube. And concentration of HCl is equal to 1 molar. The volume of NaOH is also 0.1 decimeter cube. The T final is 26 degrees Celsius, and T initial was 20 degrees Celsius. The density is assumed to be 1 gram per centimeter cube, and the specific heat capacity is 4.2 joules for every degree Celsius. So if you want to answer this one, we need to find the delta H by dividing the total quantity of heat Q over the number of moles. And this should be by negative because this is an exothermic reaction. Neutralization reactions are all exothermic. So Q is equal to MC delta T divided by the number of moles. I don't have the mass, I have the volume. The volume of 100 ml plus 100 ml is 200 ml total of the solution. And if you want to change this into mass, density is equal to mass over volume. So mass is equal to density multiplied by volume. So the density is 1 and the volume is 200. So the total is 200 grams. Now change it 200 milliliter into 200 grams. So negative 200 multiplied by the 4.2 specific heat capacity multiplied by the change in the temperature. 26 minus 20 is 6 degrees Celsius. And we'll divide this by the number of moles. But what is the number of moles? Number of moles, concentration is equal to number of moles over volume. So number of moles is equal to concentration multiplied volume in the solutions. The concentration is 1 multiplied by the volume. But for which solution, or for both of them? For the limiting reagent. And both of them are in equivalent ratios because this is 1 multiplied 100 and 1 multiplied 100. So there is no limiting reagent. So we'll choose any of them. The concentration of it is 1 and its volume is 0.100. That's the N. So I will say that negative Q, so that's equal to delta H is equal to negative Q over 1 multiplied by 0.100. So 1 multiplied by 0.100 is 0.100. So this means that delta H is equal to negative 200 multiplied by 4.2 multiplied by 6 divided by 0.100. Wait, the result is going to come up to be minus 50400. But what is the unit? The unit is taken from here, the joules. Here I have degrees Celsius, and here I have joule per degree Celsius. And here I have the number of moles in moles. And here I have minus 200, which is the mass. So this is grams. We said this is joules per C per G. So there is a grams here. So when we cancel the unit, of course, I will not do this every time just to show you that the Celsius will be cancelled with the Celsius, the grams with the grams, and then I will have the value as joule per mole. So the result will be coming as joule per mole. But delta H, as we know from before, must be calculated in delta H in kilojoules. So I'll divide this by 1000. So it will be negative 50.4 kilojoule per mole. So 3 things I have to watch out in this question. The first thing is the significant figures. So I have 3 significant figures. That's the minimum, 50.4. And the second thing is the value. And I have calculated the value. And the third thing is the charge, because the value without the negative charge is not correct. So it's not charge, it is a negative. I mean, it's a negative. So the value without the negative, if it is positive 50.4, it's wrong. And the last thing is the unit, which is kilojoule per mole. Basic question number 2, 0.600 grams of carbon was burned with excess oxygen in a bomb calorimeter. The heat capacity of which was 10 kilojoules per degree Celsius. The temperature of the calorimeter and its content is increased by 1.8 degrees. Calculate the delta H for the combustion of carbon. Let's have a look here. The given is, this time is the mass equal to 0.600 grams, but this is the mass of what? Of the carbon, of the fuel that I am going to burn. I'm given also the capital C, which is the heat capacity. Take care, this is the heat capacity, not the specific heat capacity. So that's equal to 1.10 equal to 10 kilojoules per degree Celsius. And the temperature change, which is delta T, that's equal to 1.8. That's the final temperature minus the initial temperature, degrees Celsius. So these are all the given, and I'm required to find the delta H of the combustion of the carbon. So delta H again is equal to negative Q over 8, and like the last time, and this is equal to negative C delta T this time. So this is a bomb calorimeter, and there is a fixed volume, so I don't use MC delta T, I just use C delta T. And then I divide this by the number of moles. The C is equal to minus 10, as we said in the given, and the temperature is 1.8. There's a difference in the temperature. The unit of the C is kilojoules per degree Celsius, and this is degree Celsius. And the number of moles is equal to the mass of the molar mass. The number of moles of the fuel is equal to its mass by grams divided by its molar mass, which is 12. So if we divide with 10, so if we divide with 0.600 divided by 12, you will get the mass divided by the molar mass, so that's equal to the number of moles. Then you divide 0.600 divided by 12, and the answer will be in moles. So what will be the unit for you? The unit will be cancelled. It will be kilojoules per mole because you will cancel the delta C with the delta C, and this is in kilojoule. So it will be in kilojoules per mole. So what is the answer? If we do the math, we will get minus 360 kilojoules per mole. Note that the result now is kilojoule per mole because the unit of the C here is kilojoule. And the unit last time in question number 1 was in joule, so the answer was in joule also. In basic question number 3, 3 grams of ethane were burned in a calorimeter. The heat capacity of the calorimeter is 25 kilojoules per degree Celsius. Temperature of the calorimeter increased by 5 degrees Celsius. Calculate the heat of combustion per mole of the ethane. The same thing, only the difference is that he called it in a different way. Instead of saying the delta H or the enthalpy change, he asked it to find the heat change or the heat of combustion per mole, which is delta H, because it is Q per N. So that's equal to negative Q over N again. And again, that's negative C delta T. He said the heat capacity. Whenever he is saying the heat capacity, so he means the capital T. And in this case, we will use that equation of delta H, or the Q is equal to negative MC delta T. Will not put the M here, it will be negative C delta T. And if he said specific heat capacity, if he said specific heat capacity, in this case we use a small c, so that Q is equal to negative small c multiplied by M multiplied by delta T. So here we have a bomb calorimeter. So we have the specific heat capacity or heat capacity. You have the heat capacity because it's capital C, and because he said that it is the burned in kilometer and said the heat capacity only. He did not say the specific heat capacity. So I will say that equal negative Q. So negative 25, which is the C. Let me put it here under this one. So equal to negative 25 multiply the change in temperature, which is 5. So divide the C multiplied by the delta T over the number of moles. And number of moles we'll get like we got last time, same exactly way. So it's equal to maybe 25 divided by mass over molar mass, so 3 grams. But what is the mass of ethane? Ethane is C2H6, so 24 plus 6 is equal to 3. So 23 divided by 30, let's get the calculator here. Minus 1250, and this is kilojoule per mole, or we can say negative 1.3 multiplied 10 to the power of 3 kilojoule per mole. So we did nothing different. Also the mass over the molar mass to get the number of moles from here, and Q here is the total amount of heat, which is equal to C, capital C multiplied by delta T. In the next question, he was asked to use Hess law to calculate the delta H for the reaction. So there is one reaction, it's iron 3 oxide is reacting with carbon and being reduced into iron, and carbon is oxidized into carbon dioxide. This is the equation that I need to find its delta H using two other equations: burning of carbon with oxygen and burning of iron with oxygen. So we need to make manipulation in the two equations. The first one, let's have a look. The carbon here in the first equation and the carbon here in the second equation, in this equation that I want to go to, is in the same direction. So I don't need to reverse the reaction. I need only to change one carbon to 3 carbons. So this means that I will multiply this equation by 3. In the second equation, the iron is here on this side and it's here on this side. So I need, sorry. So I need to reverse it. So Fe2O3 here is on the right and here on the right. I need to reverse it and multiply it by 2 because I need to change Fe2O3 into 2Fe2O3 or 2Fe into 4Fe. So I need to reverse it and multiply it by 2. So multiplied by negative 2. So this one multiplied by 3 and this one multiplied by negative 2 and then add them together. Let's see the mass. So delta H is equal to this one multiplied by this one, and the result will be negative 470 kilojoules. So again, I multiply this number by 3, multiply this number by negative 2, and found the result. Another way to do this is to find the delta H of formation of products minus the delta H of formation of reactants. So when I formed the products, when I formed the carbon dioxide from its reactants, which is carbon and oxygen, I used the minus 390 kilojoules. That's for every mole, but I need 3 moles of carbon dioxide to be formed. So minus 390 multiplied by 3. And then what about the iron? Iron is element. Its delta H of formation is equal to 0. So if I look the values of the delta H of formation of carbon dioxide equal to minus 390, how did you know? Because here it says that when I made the carbon dioxide from carbon oxygen, I needed minus 390 kilojoules. And the delta H of formation of Fe2O3 from its elements is equal to minus 820. That's the reactants, right? This is the reactants. So minus the delta H of formation of reactants multiplied by 2 again. So 2 multiplied by minus 820. Again, the carbon is just an element, so it's not added, it's only 0. So when I subtract the delta H of the formation of the products, the amount of heat I required to make the products minus the amount of heat I needed to make the reactants from its reacting substances, from its main substances, from each original. When I need CO2, CO2 is made from what? It's made from carbon and oxygen. Fe2 is made from iron and oxygen. Then I will make the subtraction. It will be the same value. It will be, sorry, I said minus 470, it is plus 470 kilograms. The next question. Gases hydrogen and fluorine combine to form hydrogen fluoride H2. Reacts with F2 to form H2F. 1 mole of hydrogen molecules reacts with 1 mole of fluorine to form 1 mole of hydrogen fluoride. The enthalpy change for this reaction, delta H, is equal to minus 540 kilojoules when you make enthalpy change means when you make 1 mole of hydrogen fluoride. So what is the heat of formation of hydrogen fluoride? Mister, isn't this the same thing? You have formed the hydrogen fluoride from its reactants. So hydrogen fluoride is made from H and F. And now you are asking me the same question. So what is the difference? What is the value of heat of formation? So you are asking of forming again HF from H2 and F2. The whole answer lies in the definition. What is the definition? The first one he mentioned, minus 540, is not the enthalpy change of formation. It is the enthalpy change of the reaction. This is the value. Enthalpy change of reaction can be 1 mole, 2 moles, anything, 3 moles. So it's equal to minus 540. But when he says what is the value of heat of formation of hydrogen fluoride, means the formation of 1 mole. So in this case, I have to divide everything by 2. This is divided by 2, this is divided by 2, this is divided by 2. Why? Because this is the enthalpy. This is the heat of formation of hydrogen fluoride, not the enthalpy of reaction like this one. So basically, it looks the same, but the only difference is that here it has to be per 1 mole only. So delta H also will be divided by 2. So that's minus 540 divided by 2. So we'll divide this, will be delta H is equal to minus 270 kilojoules per mole. In the next question, find the delta H of the reaction. So the delta H of the reaction is the delta H of the delta HR. So if I am making C3H8 reacts with 5 oxygen to form 3 CO2, how much heat is produced per mole in this reaction? But when I say reaction like the last question, it means even it can be 3 moles, 4 moles, how many moles reacted, it doesn't matter. So the delta HR, like in the last question, is the delta HR in basic question number 5. Here it means the enthalpy of the reaction, whatever the number of moles is reacted or formed. So I have the values of the delta H of formation. Do you remember how did we get the delta HR from the delta H of formation? We said that's the delta H of formation of the products minus the delta H of formation of reactants. How much heat was needed to form the products, which is carbon dioxide? I needed minus 390, but for how many moles? For 1 mole, and here I have 3 moles. 3 moles. And water, I needed 4 moles of water, so 4 minus 286, that's to form the products. Then I will subtract this from the heat that was required to form the reactant. The reactant is C3H8. I needed minus 100 kilojoules to form the C3H8, and oxygen is an element, so it's not calculated here. It's 0. If you want to write it, to show me understand, it's equal to 0. So if I make minus 390 multiplied by 3 plus 4 minus 188 minus 100, the result that I will get is equal to minus 100 kilojoules. If you don't understand where did this come from, let me tell you, this is all from the Hess cycle. Hess cycle is telling that if you go from here to here, or you go from here to here, you remember the cycle? So if you go from A to B, it's the same like you are going from A to C, then C to B. So delta H1, which is the amount of heat needed to go from A to B, is equal to delta H2, that's going from here to here, plus going from here to here. Why? Because going from here to here is equivalent to going from here then to here. So if you move from A to C, then C to P, and added these two together, which is delta H2 and delta H3, so delta H2 and the delta H3, it is equivalent to the same heat like we are going from A to B, that's delta H1. Okay, what about the formation? Delta H of formation of carbon dioxide means I needed to form carbon dioxide from carbon and oxygen. Or carbon and oxygen. When it formed carbon dioxide, delta H of formation of carbon dioxide minus 390 kilojoules. But this is for 1 mole, so multiplied by 3. And this is minus 286 multiplied by 4. So in order to make this one and this one, I needed this one and this one of heat. And when I needed to form the C3H8 from carbon and hydrogen, I needed minus 100 kilojoules. So again, if you want to go from here to here, which is delta H1, that's equal to delta H2 plus delta H3. But wait, isn't delta H2 should be going from here to here, not the opposite? Yes, should go from here to here and then here to here, like the red. But actually, I don't have the red. I have the black. Why? I have the formation of CH8. That's why the arrow is going up. So because the arrow is going up and I need to reverse it, I need to go red, I have to reverse the values. That's why I get the negative 100 and make it minus because I have reversed it. What about this one? I didn't need to reverse it, right? So if you want to say delta H1 is equal to delta H2 plus delta H3, yes, I can say delta H1 is equal to delta H1 is equal to delta H1, which is this one, equal to delta H2, which is this one, but reverse it. So it is minus delta H2 plus delta H3. I can just shift these two together, make it delta H3 minus delta H2. So actually delta H1 that's required to find is equal to delta H2 reverse it minus delta H3, which is not reversed. So I just changed the values. So minus delta H2 plus delta H3, I put the delta H3 positive and delta H2 minus. What is delta H3? It is the heat of the formation of these two, which are the products, minus the delta H2, which is the heat of the formation of the reactants. Okay, if you find that this is confusing, just do delta H of the products minus delta H of the reactants. Take care of the signs very well. See you in the next video.